In this video, we're going to take a look at the theory of circular motion, and we'll start from a really simple picture as you're seeing right here, where we just have an object going around in a circle at constant speed. We're looking at this from above. Maybe this is a marble going around some type of circular hoop or something like that. And I want to go from the most basic idea, which is that at any given moment in time, we can draw a velocity vector that's tangent to the circle as shown here, and go from these two vectors all the way up to the theory of circular motion in terms of centripetal force, centripetal acceleration, and then how we actually solve problems. So we're going to be doing some vector math here and really trying to understand at the ground level what's needed for circular motion. So let's get started. Now the first question is a simple question, and I want you to think about it, and it's this. Is this object accelerating? Write it out here. So pause the video. And remember that this object is moving at a constant speed. I'll write that over here. That's going to be the assumption here in our little example. Is the object accelerating? Yes or no, and why? So pause the video and see what you think. All right, well, the answer is yes, most definitely. And it's because the direction of the velocity vector is changing. Now, the magnitude of the velocity vector is constant. That's the speed part of velocity. But you can see the direction is rotating around. It's always tangent to the path. And so, therefore, the object is accelerating. Now, it's important to see where that comes out through the vector math. And so let's do that now to prove that it is accelerating here just by doing the vectors. So in order to do that, we're reminded that the acceleration as a vector is equal to, and technically I guess this would be an average acceleration, but if we assume a small enough kind of time scale, then this would, in the limit, go to the differential calculus version, which we're not going to do. But just imagine that this time that exists in between here is pretty small, so we can kind of approximate there. And let's just do what this math says. We want to construct the acceleration vector right here. And in order to do that, it looks like we're going to need to first construct the change in velocity vector. So give this a shot and try to draw out on your page, on your paper, the change in velocity vector. So convert that language into a mathematical operation and see if you can get it right. Pause the video and draw the change in velocity vector. Let's take a look at the answer here. And the key skill is converting the language into a mathematical operation. So whenever you see a change in, as you do right down here, that is a subtraction problem. Change in what? Well, it's the change in the velocity vector. So you just write that out. Change in the velocity vector is the final velocity vector minus the initial velocity vector. And we've chosen, two vectors here to show a little bit of rotation in the direction, so we can actually solve it. So let's do that. How do we subtract two vectors quickly and easily? I would recommend you use the tail-to-tail method. So you just draw the two vectors tail to tail. Oops, that one's a little bit too long. That's okay. I'm just going to go like this. There we go. This is V initial over here, and this one is V final. And then you always go from where you started, V initial, to the final one. So it would look something like this. And that would be labeled your change in velocity vector. Just simple vector subtraction. So you can see now we've constructed it, and it points to the left, but a better way to talk about that would be that it points inwards like this. So I'll label this as delta V. Okay. Got this little delta T still hanging out over there, but this line is the change in velocity vector. So notice that it points inwards. Okay. Now, how do we connect this to acceleration? There's, two things that you want to think about. Every vector has a magnitude and a direction. So how would we use this change in velocity vector to get the size of the acceleration vector? And then what direction is this acceleration vector in? Is there any information that we get from the change in velocity vector that can tell us that? Pause the video and try to now construct or write out how you would construct the acceleration vector from information that's on the screen right now. Give it a shot. All right, so we need to be reminded of an important mathematical fact, and you can see that over here on the right-hand side. And that fact is that when you want to construct a vector out of another vector, you can do so pretty easily with what is called scalar multiplication. So here's an example. We want to construct the vector g out of the vector b. And I've drawn the vector b as just a single arrow to the right here of some size. And if vector g is 3 times the size of vector b with scalar multiplication, then you just add up b 3 times using simple vector addition, and now we get vector g. So vector g would just be a vector that is this line here. Let me actually just draw that out. So this would therefore be vector g. Okay, but what's really important for you to notice is that the vector that gets constructed out of another one is parallel to the original vector here. This scalar multiplication doesn't change in any way the direction of the vector, as you can see in the picture, so it's parallel. So what that means then in the context of physics over here is that the acceleration vector is parallel to, what those two vertical lines mean, the change in velocity vector. Now that's important because we have already determined the direction of the change in velocity vector over here on the right-hand side. How did we do that? Well, we use vector subtraction from the definition of what change in something means. And so we see that the change in velocity vector pointed inwards towards the center of the circle. So guess what? Acceleration is parallel to that. So therefore, we can now say very easily that the acceleration vector would look like this. It would also point to the left. Cool. The only other thing we would want to know to actually construct the amount of acceleration in terms of magnitude would then be doing the scalar multiplication. So we would need some information about time over here. You can see that up here. And either the acceleration vector would stretch or contract, sorry, the other way around. The change in velocity vector would either get larger or smaller to produce the acceleration vector. The units, of course, would be different. So you'd have meters per second squared for the acceleration vector versus meters per second for the change in velocity vector. So since we don't have numbers, we won't do that, but just realize that the size of the acceleration vector may be a little bit different than the change in velocity vector if your time is anything different than like 1 second. 1/1 is just 1. So, all right, so I've kind of redrawn some things over here. And just a technical point, we're kind of approximating, and what you would want to do technically is take the limit as that time interval goes to 0 with some calculus, which we're not going to do. But as these two things kind of get closer and closer and closer, you approach this acceleration vector right at this moment in time, which would be pointing totally inwards to the left, I guess, if you will, parallel to this axis. And therefore, you know, at some instant in time, you can define the acceleration as always inwards. It's always the same magnitude for the acceleration, assuming this is constant speed around a circle, which we're going to assume right now for our problem. You always have the acceleration vector pointing inwards towards the center of the circle. Now, another really cool way to kind of think about that is seeing how the velocity vector is changed by the acceleration vector. So let's do that real quick. You get one more little abstract way to see what's going on with all the vector math. So let's go into a little bit more depth on that rotation of that velocity vector. You can see here that I've got this ball at some moment in time. I'm just calling that some initial moment in time. The acceleration is totally inwards, and notice how it's perpendicular to the velocity vector at this moment in time, as drawn down here below. Now, what I want to try to show is how this velocity vector is going to rotate a little bit. So it's going to be pointing kind of up and to the right a little bit at this final location, which is a little bit later in time. So how do we do that with all of the vector math? It's really nice when you can see this. So what you would do is you'd go to first principles and you'd say, well, we know by definition that this is true. The acceleration is the change in velocity vector divided by a change in time, right? So start playing around with that. You can write out maybe that the change in the velocity vector is the acceleration vector multiplied by the change in time. Just doing some algebra there. Then we could expand out the delta, and we'd realize that the final velocity vector minus the initial velocity vector must be equal to the acceleration vector times some small time interval. And then finally, we can solve for the final velocity vector here. And let's see what it gives us. Well, it tells us that we get the initial velocity vector plus some other thing over here. And we'll put a box around this and then use this in our reasoning now to kind of show that rotation of the velocity vector as we go in a circle. All right, so if you look up here, I just rewrote the equation at the top right, and it's just vector addition. So we want to be able to produce a final velocity vector after some time has occurred. You're seeing that down here over this time interval. And the information that we need is an initial velocity vector. We certainly have that, so we can redraw that over here. So we'll redraw that here. And then we need to add to that something, right? What is that something we need to add to it? Well, it's a little bit more than the acceleration vector. Watch out. It is the acceleration vector, but multiplied by that small time interval. And if you come back over here, that's just the change in velocity vector. Now, in our previous part of the video, we showed how those vectors were parallel. So we can go ahead and draw that. And I'll go back to that color I was using before. And I'll draw that here. And so this is going to represent the acceleration vector multiplied by that scalar delta t, which again was the change in velocity vector. So the size of this vector right here, this one, it's going to be a little bit different than the size of this actual acceleration vector in the picture, unless you're using like 1 second or something for your choice. But when you're doing this problem and you're assuming a really small time interval, then it's probably not going to be that way. But oh well. Anyways, now we go from where we began to where we finished. And we'll do that. So here's where we started. We're doing just simple vector addition to where we finished like that. And now I would label this as my final velocity vector. And so you can see the rotation effect that's occurred. Now we have a vector that looks like this. And it hopefully gives you that sense of why that acceleration needs to be inward and also always perpendicular to the velocity vector at any given moment in time as we go around this. So all the acceleration vector ever does is it just changes the direction of the velocity vector through this little approximation mechanism here. Again, you'd really have to kind of take the limit as something goes to 0 and do the calculus, which we're not doing here, but you're kind of seeing an approximation of that idea. I mean, obviously you can see if this is a right triangle, this one would be a little bit longer than that one, right? But take the limit as something goes to 0, do all the calculus, and it works out perfectly fine. So we won't do that. All right, now that you see that, moving forwards, we can start to talk about, okay, so this is great. There's an acceleration, but we know that something causes accelerations. What causes accelerations? Pause the video. In the back of your mind, you should immediately know what causes the acceleration for any object. And remember here, this is important. This is kind of our first example of seeing how when something is accelerating, it's not necessarily speeding up or slowing down. In this case, it's just changing direction. Interesting, right? So think about it. What causes accelerations? And we'll see. All right, so here's the answer. Hopefully you got it. Net force causes acceleration, always. One of the most powerful laws here in physics. Now, not only that, and you can see how I've written down Newton's second law in this way, but we can also notice that because of the vector math, in a very similar way to before, we've got a vector here, and then a scalar. So it's just scalar multiplication. If you know something about the net force vector, then you can scale that up or down based on 1 divided by the mass, and then that will produce the acceleration vector, of course, with the right units. But importantly, the acceleration vector now, in the same way, is parallel to the net force vector. So immediately we can see that what causes this circular motion, working it all the way up from just thinking about velocity vectors and doing vector math, is that the net force causing that motion has to be parallel to the acceleration vector and therefore always inwards towards the center of the circle. So we've just effectively kind of proven that for something to go in a circle, you need a net inward force. So I've just drawn a little picture over here, again, the view from above, and you can see at all these little moments in time as this ball goes around, say, a hoop here on a table, we're looking down on it, that there's a force inwards, always pointing towards the center of the circle. The magnitude of that force doesn't change at all. The acceleration magnitude doesn't change at all, but the direction of both the force vector and the acceleration vector certainly change, as we have just seen. All right, so what's left to do next is just to kind of invent some terminology that we typically use to talk about this type of motion, and then also incorporate Newton's second law so we can get a mechanism by which to solve problems, and then get used to a new coordinate system that we use in circular motion as well, called the radial direction. And we'll take a look at all those things now. All right, so let's take a look at this picture over here on the left. First of all, the new direction I'm talking about is called the radial direction. And it's very easy to draw. There's an infinite number of radial lines you could draw around a circle, and it's just a line that goes from the center of the circle out to the object along the radius. So it's called a radial line. And so that defines the direction then, and is much more useful than x and y that we've seen before. So for this object, and again, we're looking above, keep remembering that in all of these examples. We're watching a marble go around a hoop or something on a table. And with this directionality, we define inwards to be positive and outwards to be negative. We'll see how that comes to play, but it's just something that you need to know in order to solve problems correctly here. Now, importantly, we just built up this idea of this inward force coming from, velocity vectors and then acceleration. And for something to accelerate, it needs a net force on it, right? Now, a net force is not like an additional force. A net force is the summation of actual real-world forces from objects being exerted on the object in question that's moving here, right? So this force that I've drawn, this force vector, represents the net amount of force that this ball is experiencing. And we call that net inward force in circular motion the centripetal force. Centripetal with a P. Notice that. It's not centrifugal with an F, it's centripetal with a P, and that has the meaning of inward. Centrifugal means outwards. And there's another way to analyze circular motion at a little bit more advanced level in the reference frame of the thing that's accelerating, and you use terminology such as centrifugal or centrifugal, and we're not going to be doing that. So centripetal is how we will describe this net inward force. Centripetal with a P. Okay. All right, so now that you can see that, this begs the question, what are the actual forces causing this? And it could be anything, really. I'll give you a simple example. Imagine that this ball has like a rocket thruster on it or something like that, which would be quite hilarious. And it's, I don't know, let me just draw it up here. So here's the ball, and then it's like literally shooting out rocket thrust, right? So if it did that, you could imagine that there would be a force pushing the rocket this way, right? So that's pretty easy to imagine. But what if we actually directed that rocket thrust backwards like this? Okay, well, then there would be a force that way, outwards, right? So, for example, if this was like a hoop, like some metal hoop or something, then we'd really have two effects here. We'd have the force from the hoop that would be coming in like this. I'll label this force of the hoop. And then if we had this kind of fictitious rocket thrust, kind of hilariously going like this, right? You can see that that would be an outward force on the ball. It would try to push it out of the circle. And so I'll draw that here. I'll just use the same color like that. And so there's our thrust from the rocket. Or it could be a magnet, it could be anything, it doesn't really matter. I'm just kind of using a rocket thrust as an example. Okay, so you can see that there's like these two competing effects. We've got the hoop that's pushing inwards towards the center of the circle, but then we've got this random outward force because the ball has a rocket on it or something. But importantly, this is the whole idea of the unit that you really need to understand. It's that there has to be a net inward force for this thing to go in a circle. And you can see how I've drawn the vectors. I've been very careful to show you here that there is more inward force than outward force. To put numbers on it, maybe this is, I don't know, positive 10 newtons, and maybe this one over here is negative, I'll just put the magnitude, 7 newtons. And then we map the coordinate system directionality here, positive is inwards and negative is outwards. And we can now calculate the net amount of force. Let's do it together, and let's also throw on some terminology that's important. So what we do is we add up all of the, well, what should we call this? All of the radial forces, because that's what they are. They're forces that are parallel to the radial direction. And when we do that, we get plus 10 newtons, it's the first force, plus a negative 7 newtons, remembering that negative is outwards, and we end up with positive 3 newtons of net inward force. Great. So therefore, if we kind of go to the other little picture over here, I'd have to change the length of my arrow right here. This is a little bit too long compared to these force vectors to show the correct relative magnitudes, but just so I don't have to erase that, I'll just put 3 newtons over here. And so you can see now on the right-hand side, we've got this picture of the actual individual forces that this ball feels. One comes from a hoop, the other comes from a rocket thruster. But abstractly, we add those together, and then that creates this thing called the centripetal force, or the net inward force. And importantly, let's be very clear about this, this is not another force, or another actual force, if you will. There are not 3 forces being applied on this ball. There are only 2 forces being applied on this ball. Added together, there's a net inward force of 3 newtons, and therefore we go in circular motion. So just watch out. The common misconception students have when first learning this is that the centripetal force is like this third special force or something. It's not. It's just the abstract addition of the actual forces. Now, you don't have to have 3. You could come over here and you could have 4, 5, 6. You could have 20 forces exerting on this ball. It's just that you better have more inward than you do, more larger inward forces as a whole than outward forces to get circular motion to occur. Okay, so terminology-wise, you can see all of these things mean the same thing. Add up all the radial forces, sum them together. That is, by definition, the net inward force. And then that also, by definition, is what's called the centripetal force, or just FC for short. Now, to make all this a little bit more compact, what you can do is just write out Newton's second law. And we know that if there is a net force, it better be equal to mass times acceleration. But because we have this new terminology, we can call that the centripetal acceleration. So there's a couple ways to do this. And I think the way we'll just write it out here right now is that the centripetal force, which is the net inward force, is equal to mass times the acceleration. Because of Newton's second law, that's all this is. There's nothing new here. It's just the second law. But we do put a little c there for centripetal. So this is called the centripetal acceleration. Now, we didn't really mention that word in the beginning of the video. We just called it the acceleration. But now we have this defining word, centripetal, to keep reminding that we're talking about the inward acceleration that we had shown before. All right, so we're almost there with getting the final theory here that's going to allow us to solve a lot of problems. Next little bit of terminology is what's called the tangential velocity. So we've been talking about these velocity vectors, initial and final, but in general, you just call the velocity vector at any moment in time that something's going around in a circle like this, the tangential velocity, because it's tangent to the path. And you can see that in the picture here. So v sub tan, I guess, if you will, doesn't have anything to do with like taking the tangent of an angle. It's just tangential to the curve. So it just intersects it at one point like that. So I've drawn an image. Again, this is the view from above. We're watching a ball go around in a circle. We now know that we have acceleration pointing inwards. We have the centripetal force, which is the net inward force pointing inwards. Just kind of separated them out a little bit so you can see them. And then the tangential velocity vector. So these are all vectors, and they're all different vectors, by the way, but there's relationships between them. Now, let's talk about the centripetal acceleration in a little bit more depth here, because there is a way you can obtain that value, the magnitude of it, by looking at the radius of the circle. So I'll just put this as r, and then the tangential velocity. And it's pretty easy. I'm not going to prove this here. It would take a little bit more than I want to do in the video, but you can certainly read in a book about this proof. It's a fun geometric proof. But the idea is that the centripetal acceleration is going to be equal to the square of the tangential velocity divided by the radius of the circle. It's a really important formula to know. And in general, this is just the magnitudes. So if you want to get the magnitude of the centripetal acceleration, you would square the tangential speed and divide by the radius. So everything's going to pretty much end up being positive here. Now you don't need to get bogged down in any vector math here like we did before. It's just plugging in numbers for how fast you're going in meters per second, dividing by some radius value, typically in meters, and then you get your centripetal acceleration value. All right, so very important formula. Now, what do we do with it? Well, ultimately, we want to be able to use Newton's second law. However, nobody wants to find the acceleration always. I mean, you can if you want to, but it's a little cumbersome. More often, you want information about how fast the object's going, the tangential velocity, and you have that information. So we can write down now Newton's second law using this. So let's do that. It's pretty easy. We know that Newton's second law says that the centripetal acceleration, or the net inward force, is equal to mass times centripetal acceleration. What do? I'll let you pause the video and finish the formula here and see if you can get it. All right, so here it is. You can see what we've done. We've just plugged in the tangential velocity squared divided by the radius for the centripetal acceleration and created our equation. And what I like to do is make this a little bit more process oriented, and we'll write out that the sum of all of the radial forces, which again is the centripetal force, which again is the net inward force, is equal to mass of the object times the tangential velocity squared divided by r. A lot of times you'll see this tan left off there because it's implied from the context, but we'll leave it on here for this video. And there you have it. This is Newton's second law for uniform circular motion. And this will allow us to solve a bunch of problems where we have an object going around in a circle. It has some tangential velocity, a radius r, and then we can apply that. So we'll do an example and see how this can be applied. Still meters per second squared. To make sure you can apply this, pause the video, and I'd like you to calculate these three things from the picture. Calculate the centripetal force on the object. It's a 3 kilogram object over here. Calculate the centripetal acceleration, and then the tangential velocity. I've drawn some forces over here. Let me just kind of cover up that object all the way. So there's a ball going around a circular hoop, and for whatever reason, we do not care at all. There are three forces being exerted on it. They could come from magnets, they could come from rocket thrusters, they come from anything, contact or non-contact, it doesn't matter. But there are three of them, and then you need to figure out all of the things based on that. So give it a shot. Pause the video and try to get every single one of these things right. It's not too hard of a question here. There's a lot of new terms, etc. This is an easier level question, but you need to be able to obviously know how to do this to get to the harder ones. So give it a shot. All right, question 1. By definition, the centripetal force is the summation of all the individual radial forces. We add them up and we make sure to not make a sign error. So outwards is negative, don't forget that, and inwards is positive. And so you get 5 plus 2 plus a negative 4. And so that gets you, let's see, 7 plus a negative 4. Did the math correct, and it gives you a positive 3. So there's your centripetal force. There are 3 newtons of net inward force being exerted on this ball, causing it to move in a circle. Let's look at the next one. All right, now you might have been tempted to solve for the tangential velocity, or you might have got tripped up a little bit to figure it out. And you can find the centripetal acceleration very easily by just using Newton's second law. So we get the centripetal acceleration is equal to the centripetal force divided by the mass. So 3 newtons of centripetal force divided by 3 kilograms gives you 1 meter per second squared for your centripetal acceleration. Now down here I've written this as 1 meter per second for every 1 second. And that's how you can obviously say acceleration without saying the word squared or per. So 1 meter per second for every 1 second. And it's tempting to think that that is speeding the object up or maybe slowing it down at some rate. But remember, that's not what's happening. Because the acceleration vector is perpendicular to the tangential velocity vector at all moments in time, there's no speeding up or slowing down with the vector math like we showed. It's a rotation and it just changes the direction, which is quite interesting. Right, so you can go rewatch that again or work through that. Just watch out. There's no speeding up or slowing down here. However, the units are still meters per second squared for acceleration, which is interesting. All right, so now the final part to find the tangential velocity, I've deliberately done something that I see students do all the time when writing up solutions to physics problems, which is very poor practice. And you can see, if you just look at the math, you could probably piece together the calculation I'm doing with solving for the tangential velocity. But what a student might do if they're trying to do this problem quickly or something is just go right to plugging in numbers. They didn't solve for the tangential velocity in variables. They didn't even write out the equation in variables, the first principle, and they didn't put any units in there. So this is not good. Let me cross this out. Avoid doing that and instead take the time to clearly communicate what you're doing. So let me model that. You'd write out acceleration, centripetal acceleration is v tan squared over r. That's my first principle. That's what I know to be true. And I haven't plugged in any numbers yet. Now I'll solve for what I need to solve for, the tangential velocity. So I'll do that here. V tan squared is equal to acceleration centripetal times the radius. And this is such a simple algebraic problem. You probably don't need to annotate every little step here. But anyways, now we take a square root. And now we're ready to plug in our numbers. Now sometimes the formulas get so cumbersome and there's so much to do that it might not make sense to solve it all in variables till the very end. But most problems that you do solve in physics, you're doing everything in variables and you're getting solutions like that. So I recommend you hesitate to plug in numbers until the very end, keeping it in variables as long as possible. So we'll take a square root here. We'll plug in our numbers with units. So we get 1 meter per second squared here. And then we need to multiply this by the radius, which is 0.5 meters. Notice what happens when we actually plug in for the units. We're going to get the square root of 1 times a half is a half, and we get 0.5, but the units are meters squared per second squared. And because we're very careful with all of this, we can see that when we take the square root of meters squared over second squared, we're going to get the correct units as our answer. And so you get the square root of 1/2, and then meters per second would be the units. I'll write the answer over here since I'm running out of room. So our tangential velocity is equal to 0. And I'm going to round just to 2 decimal places to make it easy to look at, 0.71 meters per second. So that's how fast the object is traveling. That would be the length of the tangential velocity vector. So I'll draw that up here as well. We don't really know which way it's going because I didn't specify. It doesn't really matter, but this would then be v tan up here. Awesome. Okay, now take a step back, and if you just look at this and reflect on everything we've done here, notice how we've got a lot of different vectors, 3 of them really. You got centripetal force, centripetal acceleration, and then tangential velocity. And you have to keep them all straight in your mind. Remember that velocity is different than force. Those are different concepts. Acceleration is a different concept than force, and it's also different than velocity. And then we now have this mechanism by which we can calculate all of the things in a problem. The next step from here would be to do some more advanced problems just in variables, where we're really using these concepts and the tool of Newton's second law as a guide for our thinking that allows us to understand more abstractly what a certain system would do. So a good example of that might be a ball being twirled around on a string, or maybe, as and we'll see this, a flying pig going around in a circle hung from a ceiling. They get these little toys called flying pigs, and they go around in circles, and that's a classic problem. Or maybe a roller coaster. You could have an object going around a roller coaster loop and analyze the situation maybe at the top when you're upside down, or at the bottom when you're at the bottom of the roller coaster. And these concepts can help us understand things abstractly in variables. So we'll move forwards into that more challenging material, but hopefully now you get a good sense of the basics and how to do things in a numerical way in circular motion. Take care, and we'll see you next time.